Good morning, everyone. My name is Shubhang Kulkarni. I'm a second year PhD student from the University of Illinois at Urbana-Champaign. Today, I'll be talking about polyhedral binary decision diagrams, which are new data structures for representing non-convex polyhedra. This is joint work with Michael Cruz from Argonne, and I'm very excited to be here, and I really hope you enjoy the talk. All right, so our story begins with the polyhedral model. So these are powerful abstractions for representing programs using Polyhedra. So as a very simple example, if you consider the program on the left, which is just a nesting of two for loops, you can compactly represent the statement domain, which is the domain for the iterators, using affine inequalities that come from the bounds of these iterators. And a visualization of these inequalities tell us that the statement domain is actually can be represented as a polyhedra. So every point in the statement domain corresponds to an integral point in this polyhedra. So polyhedral model can be used for program analysis and for statement scheduling. So program analysis is checking the legality of a program transform. So for example, like interchanging loops from the previous slide. Or it could also be used for statement scheduling, which is trying to form a better statement schedule according to some objective function. Maybe you would want to increase parallelism or data locality. In the latter, you would need to solve an integer linear program, and in the former, you need to solve a system of linear inequalities. So this brings us to our crucial requirement for the polyhedral model, which is convexity. So the statement domain must be convex if you want to compactly represent it as a polyhedra. You can't directly represent programs or abstract away programs using polyhedra with, say, conditional statements. That's because the statement domain becomes non-convex. So for example, if you consider the program with just two nested for loops, where say the iterators have independent domains. And on the right, if you consider the program, same program from the left, but over here, we've added a non-trivial conditional statement. Then the statement domain on the left is actually, you can represent it using a polyhedron, but the statement on the right is non-convex because in particular, it does not contain the point 3, 3 because of the conditional statement. And so we know that any interesting program would have conditional statements. So we need a way to actually represent non-convex vector sets. And currently these vector sets are represented using the union of convex polyhedra. And this is simply, as the name suggests, you decompose the vector sets into various polyhedral sets. This representation need not be unique and can also be overlapping. So if you look at the example from before, these are a few decompositions into polyhedral sets. This brings us to our motivating example for this work. And consider a program. If you consider a program with, say, 3 nested for loops, whenever I start introducing conditionals into this program, I'm basically intersecting the statement domain with a non-equality constraint. So non-equality constraints aren't affine constraints. They in fact have to be represented. There are actually two affine inequality constraints, like less than and greater than equal to. So if I consider a program with 3 nested for loops, and then its statement domain is simply a cube. So the dimensions here are the iterators, so I, j, and k. Now, if I intersect this domain with, say, a constraint of the form I not equal to p0 for some parameter p0, then essentially I'm intersecting this polyhedron with a hyperplane and saying that all the points on this hyperplane are invalid. Okay, so I equal to p0 hyperplane is invalid. and that corresponds to this continue statement. If I do the same thing for J, then I'm intersecting both of these slices of our original polyhedron with another invalid hyperplane. And so that slices our current structure into 2 more polyhedra each. So I'm left with 4 polyhedra. And if I do the same thing for K, then I once again slice all 4 polyhedron, again, each into 2 parts, and I'm left with 8 polyhedron. And of course, this argument can be generalized, and to show that if I had P such conditional statements, then the union of convex polyhedra representation would in fact require an exponential in P number of polyhedra. This is infeasible to even write down for polyhedral optimizers when P is equal to 20. And we're going to be focusing our attention on Poly, which is LLVM's polyhedral optimizer. Here, a typical execution of Poly involves representing programs via first the polyhedral model, then performing several set operations on these polyhedrally represented sets, and then finally solving an integer linear program on these sets. Under the hood, Poly uses the integer set library, or ISL, to handle polyhedral computations. And ISL uses the union of convex polyhedra representation to represent non-convex vector sets, just as we discussed. So this brings us to a problem where Poly terminates without optimizations when reaching complexity limits to keep its compilation time down. And there's two such complexity limits. So one is the maximum number of members in the union of convex polyhedra, which we saw can reach exponential, which has a lower bound of being exponential in the number of non-equality constraints for such programs. And also there's a upper bound on the number of base operations as internally done by ISL. And this limit is already reached when in the previous program with just 3 continuous statements. So the natural question to ask is there an alternative representation that avoids both of these blowups? And our work takes a very affirmative, a big step in the yes direction for this question. In particular, we give polyhedral binary decision diagrams as an alternative representation for non-convex vector sets. We give a proof of concept implementation of this data structure in Python. And we give several case studies that compare scaling behavior of common set operations, which Poly requires, where the comparison is between our PVDD implementation and ISL's union of convex polyhedra representation. Okay, and a few remarks that I'd like to make here for our data structure is that we introduce this data structure for representing and performing set operations. We want to make these 2 problems feasible for several interesting programs. So in particular, the program representation for our motivating example has a linear size PVDD representation, whereas if you recall, the union of convex polyhedra representation had exponential size. So this linear size is in the number of non-equality constraints. Because of this, several set operations become computationally and algorithmically simple, and performance-wise, they become tractable. And this is particularly useful in sets when all of these operations result in simple sets, but Poly currently terminates prematurely due to like representational overhead. We leave the question of adapting our PBDDs to work with integer linear program solvers as an open question. Our primary goal is to provide a data structure so that Poly can even reach the point of having to solve an integer linear program. Currently, it just terminates prematurely on all of these programs. So now we'll come to our data structure, and it's actually motivated by binary decision diagrams that have been considered in literature. These are used to represent Boolean functions. So if you, I'll introduce this by an example. If you consider a Boolean function on the left that's represented by its truth table, you can represent this by a very simple decision tree where you go left if the input variable is 0 or has value 0, and you go right if it has if the input variable has value 1. Now a BDD is actually just a compression of this decision tree using several simplification operations. Function evaluations on both result in the same result. So for example, if I were to evaluate 0 on 0 in the decision tree, then I would start off at the root, go to the left because of the 0, go to the right because of the 1, and go to the left because of the 0. And I'm at the 0 leaf. So that means that the function evaluation evaluates to 0. In the BDD, I do the same sort of procedure where I start at the root, I go to the left because of the 0, then I go to the right because of the 1, and whenever I'm at a leaf, I just stay at the leaf. So the third coordinate 0, I just stay at 0, and the function evaluates to 0. So in this evaluation sense, the binary decision tree and BDD is the same. And so our polyhedral binary decision diagrams are inspired from BDDs. And in PBDDs, we consider the Boolean function being evaluated as the indicator of whether a point is in the polyhedral set or not. So here variables correspond to constraints, and a point in iteration space corresponds to the indicator vector of which constraints that point satisfies. Then the function evaluation remains the same as the case of the PDD. So a very simple example, if we consider our example from the previous case, program from our previous slides, then the PBDD representation is as follows. We look at the bounds on the iterators, and which corresponds to the inequalities that are required in the polyhedral representation of the union of convex polyhedral representation, for example. And we include these constraints as the decision variables in our nodes. Now, the evaluation of a point in the iteration domain is as follows. We know that 0, 1 is not in our polyhedral set because the constraint I greater than equal to 1 is directly is not satisfied. So we directly follow the false branch or the left branch in our binary tree representation, and we reach false. So this function evaluates to false, or the PBDD evaluates to false. For the point 2, 4, we know that this point 2, 4 is actually in our statement domain. And the way we can see that this PBDD captures this point is 2 is greater than 1, 2 is less than 6, 4 is greater than 1, 4 is less than 5, and 4 is not equal, 2 is not equal to 3. So we take the false branch and we come to the true point. Similarly, 3, 3 evaluates to false because all of these constraints are satisfied. Then I equal to 3 is satisfied, so we follow the true branch. J equal to 3 is satisfied, we follow the true branch, and we evaluate to false. So there are a few distinctions between PBDDs and BDDs, and also from QoSts from literature. So an assumption that BDDs have is that all input variables are independent. Now, PBDDs need not have this assumption because you could have constraints that conflict and result in, say, the empty set. However, if your PBDD was perfectly simplified, then this case need not happen. However, we allow non-simplified PBDDs because simplification steps are actually tend to be computationally intensive, and we're interested in PBDDs in the polyhedral compilation scenarios. So we actually want PBDDs to be feasible. And so QoSts are actually quasi-affine solution trees. they've been considered in literature, used to define piecewise defined solutions of lexicographic minimums of parametric polyhedra. These were in fact our initial motivation for PBDDs, but they contrast in PBDDs in the sense that they are always defined by a context-free grammar, and so are always trees instead of DAGs. And they're also vector valued, whereas PBDDs are Boolean valued. So now we can come to some simple set operations that are actually very fast, that can be made, that you can implement to be very fast using PBDDs. So let's consider a very simple operation, which is the intersect. So if you have two polyhedral sets that are represented by these two PBDDs, Q1 and Q2, your output of this operation is the PBDD of the intersection of the two sets. Now you know that any point in this intersection must satisfy all the constraints of the first PBDD and the second PBDD. So the natural way to perform intersection is to redirect all the arcs into the true node to the root of the Q2, and we get the PBDD of the intersection. Similarly, for the union, we would want to redirect all the false arcs into the root of Q2, and we get the union. And finally, for the complement, we know that any point that doesn't satisfy the constraints in Q1 should be included in the complement. And so for the complement, we just have to switch the leaf nodes. And of course, these can be implemented to be extremely efficient operations. In our main paper, we also define and give algorithms for various non-trivial set operations like emptiness check, subset check, subtraction, and project out. All of these are required by Poly while actually performing polyhedral optimization. And all of our algorithms follow the recursion plus memoization paradigm. And that's because our Python proof of concept is inherently recursive in nature, and we would like to refer you to the main paper for details if you are interested. Another note that we'd like to emphasize is that we use several structural simplifications in order to control the sizes of PBDDs. These are conceptually very simple, at least the ones that we include in all operations are conceptually simple, but they lead to big speedups. The correctness of these simplification operations follow from the Shannon expansion of PBDDs, which the details of which we refer you to the main paper for. And our experiments show that these are necessary to make representations even tractable at times. So the two simplification operations that we include for all operations are the removal of redundant nodes and isomorphic nodes, which are also used in BDD literature to simplify BDDs. And the first one allows you to contract redundant subtrees in your BDD, whereas the second one allows you to contract isomorphic nodes or isomorphic subtrees in your BDDs, so that the final output is that you get simplified versions of your BDDs. Okay, so eventually you might be thinking we have to solve an integer linear program, right? But again, I would like to emphasize that we want to we're trying to tackle the case where Poly has a hard time even reaching the integer linear program scenario. So suppose that you have consider a program from before where your statement domain was, the first iterator was from 1 through 6, the second iterator was from 1 through 5, and we had a non-equality constraint. Suppose to this program, we added dependency to perform a program transform. We added dependency Sij is dependent on Si minus 5 j plus 4. Okay, so how do we do this? We essentially were intersecting the polyhedral representation with this dependency. To do this, we had our PBDD from before. We introduced two new variables, I prime and J prime. So we perform the same, we have the same PBDD on these two variables, and we set this dependency we include as constraints between the corresponding variables that we just added. Okay, so we have three PBDDs. And the way we relate all of these together is we intersect all of these PBDDs. So all the true nodes of the first PBDD, we point to the root of the second. All the true nodes of the second, we point to the third. All right, but now with many potential simplification operations, we find that only a singleton constraint is left over, or a singleton, the dependency, there's only a single dependency that's left over. And in fact, this is represented by this very simple PBDD. Okay, and so in order to check whether a loop interchange is valid, we can just perform standard operation. We can just perform standard checks, and we find that the dependency is to the future. And so the loop interchange does not result in a valid schedule. However, we get this result without a blow up just for constructing the domain. We can get it from this simple PBDD that we get from simplification operations. And Poly keeps several other contexts separate from domains to avoid intersection that could cause a non-convex polyhedra, but all of this should become completely unnecessary with PBDTs. All right, and this brings us to our experiments. So I'll be presenting three types of experiments. The first one is the construction of our motivating example itself. So we start off with our polyhedral sets as being the universe, and we give several constraints as input. So the input size is the number of constraints. And each constraint is of the form I is equal to 0, j is equal to 0, k is equal to 0, etc. So some variable being equal to 0. And what we do in our first program is we intersect with the complement of the constraint. So I'm intersecting with the non-equality constraint. In our second program, I'm subtracting out the intersection. So I have a polyhedral set, and I'm subtracting out the intersection of I equal to 0 with that set. So essentially here also I'm constructing the same polyhedron or the same non-convex vector set. In both scenarios, we find that the PBDD representations are actually much faster to construct than the ISL representations for these polyhedra. The second type of experiments that I would like to emphasize are the simple set operations. So we've already seen the algorithmic procedures behind intersection, union, and complement. To drive home the point that the PBDD representations actually have an advantage over over the ISL representations. We also look at these operations on our motivating example. So we plot the number of non-equality constraints on the x-axis with the time on the y-axis, and we find that in each scenario, the PBDD representation performs much faster than the ISL representation. In particular, the complement is also just constant time. All right, and our final type of experiments are the project out and emptiness checks. So these are non-trivial set operations that we perform on both the ISL and PBDD representations. Here we actually find that the ISL representations perform faster than the PBDD representations when we just restrict our attention to the base operations of project out and emptiness. However, this is due to the fact that whenever we rely on complex operations such as solving system linear inequalities, which is required for, say, the emptiness check, we fall back on constructing ISL sets for small local sets and actually solving the linear inequality system that arises out of these sets. So one of our open problems is actually to remove dependency on these ISL sets, intermediate representations. However, we do find that instead of restricting our attention to just these base operations, if we consider the time of construction of these polyhedra along with the base set operation, then in both scenarios, the PBDD representation either performs better or at least comparable to that of ISL. This is reasonable to do because in polyhedral optimization, you would want the entire procedure to be feasible. So it need not be, the fact that everything becomes tractable is the interesting scenario, and it need not be the case that you just focus on one particular set operation. And yeah, our PBDD representation leads to lots of directions for future work. In particular, one that we would like to implement a data structure that does not rely on ISL's intermediate data representation. Algorithmically, we would want to increase parallelism or operational efficiency. There's a lot of scope in looking at several simplification operations, whether domain specific or generalized. Decision orderings play a huge role in BDD literature, and so trying to implement those for PBDDs would be interesting. And several other directions that you can refer to our main paper for discussions on which. Thank you very much.